In this video, we will be discussing the extent of chemical reactions. This is a completely different topic to the rate of chemical reactions we have discussed in the previous video. They are completely unrelated topics, and so many students get confused between those two topics and make mistakes on the exam. So I want to make it very clear at the start of this video. You should not get confused between the rate of chemical reactions and the extent of chemical reactions. So first, let's look at one definition. A chemical equilibrium is when the quantity of reactant and products are no longer changing. So this does not indicate that the reaction have reached completion. As long as the quantity of reactant and products are not changing, then we are in a chemical equilibrium. Many important chemical reactions we encounter in our life are actually equilibrium reactions. The reaction does not go to completion, rather they reach a state of equilibrium. I will make this more clear using one example. The production of ammonia, which is used as fertilizers. And the chemical equation looks like this. Nitrogen gas plus hydrogen gas goes to ammonia. So this NH3 is ammonia. Note I have this double arrow symbol here. So this symbol means this is actually an equilibrium reaction. So this chemical reaction does not go to completion. So based on our previous knowledge, we would expect when we have 1 mole of nitrogen gas plus 3 moles of hydrogen gas, we would expect to see 2 moles of ammonia gas. And this never happens in the real world. The reaction never reaches completion. So that's why we call it an equilibrium reaction. So what actually happens is that we have two things going on. This applies to all equilibrium reactions. We have a forward reaction. What is the forward reaction? The forward reaction is the formation of ammonia. So this is the forward reaction. So as the forward reaction progresses, so imagine we started off with only nitrogen gas and hydrogen gas. So the forward reaction would proceed. Why does the forward reaction would proceed? Okay, so this is linked with the rate of reaction theory. So although I said at the beginning of the video that those two are completely separate topics, but they are still related in some ways, or it is related to help you understand the process. So when you only have nitrogen gas and hydrogen gas present in your system, you will only get collision between those two particles. And because of that collision, we learned about the rate of reaction. There is a certain percentage of the collision that are successful. And thus, we would produce ammonia. So this is why the forward reaction would proceed. So as the forward reaction proceeds, the concentration of nitrogen gas and the concentration of hydrogen gas would both decrease because they have been turned into ammonia in this chemical reaction. And based on the theory of rate of reaction, we know that concentration is a factor. And so this would actually decrease the rate of forward reaction. Maybe I should emphasize here, this is the rate of forward reaction, because we have less collision. If we have less collision, we have less successful collision, thus the rate decreases. So this is only one part of the story. We also have another interesting thing going on. We also have a backward reaction. So this is actually the reverse. So ammonia molecules collide and then they turn into nitrogen gas and hydrogen gas again. And this is entirely possible if you recall the collision theory. When you have a lot of ammonia in your system, inevitably those ammonia molecules are going to bump into each other. And some of this collision would be successful. And when this collision is successful, the ammonia turns into nitrogen gas and hydrogen gas again. So this is entirely possible. And this is actually what happened in the real world. So since the concentration of NH3 increases due to forward reaction we have discussed earlier, we also have more collisions. And as a result, the rate of backward reaction also increases. So this is very interesting. We have an increase in rate of backward reaction and a decrease in the rate of forward reaction. So eventually, the rate of forward reaction would equal to the rate of reverse of the backward reaction. So at this point, we reached equilibrium. Because if the rate of forward and reverse reaction are the same, then we do not have any change in the amount and the concentration of reactant and product. So the concentration and amount of reactant and product remains constant once we reach equilibrium. And another thing I want to emphasize is that the forward and backward reactions are occurring simultaneously. So this is the reason why we have this double error going on, because we have forward reaction going on and at the same time we also have backward reaction. So this is the underlying theory behind why we reach equilibrium in a chemical reaction rather than reach complete completion. And now let's go to look at the rate of reaction and how to represent this chemical equilibrium using graph. So as we have mentioned before, the rate of forward reaction would gradually decrease because as the reaction proceeds, we have less concentration of reactants, and thus we have less frequent collisions, so the forward rate decreases. And as we are forming more products, we have more frequent collision between products. And so the rate of reverse or backward reaction increases. Note that this starts from zero, because at the start we do not have any product in our system. And now you see they eventually converge. And this indicates we're at equilibrium. At equilibrium, the rate of forward and reverse reaction always converges. Also be careful of the name of the axis. So the horizontal axis is time, the vertical axis is rate. The fact that the forward and reverse reaction converges when we read off from the vertical axis indicates that the rate of forward reaction equals to the rate of reverse reaction, which is precisely the definition of a chemical equilibrium. At chemical equilibrium, because the rate of forward equals to the rate of reverse reaction, overall we do not have any product formed and we do not have any new reactant or additional reactant formed. So the concentration of each and the amount of product and reactant are not changing. And now let's look at another graph. Which depicts the relationship between concentration and time. And we are still using this chemical reaction. So imagine we started off with 3 moles of hydrogen gas, 1 mole of nitrogen gas, and 0 mole of ammonia. As time progresses, we would expect to see something like this. And this graph is a little bit tricky. So first characteristic we see is that the gradient, so everything is about gradient really for this kind of graph. The gradient is flat at equilibrium. So at equilibrium, you can see that the concentration is not changing. That's why the gradient is 0. And we do not see any convergence. Unlike in the rate graph, we can see a convergence of forward and reverse reaction. Here, there's no convergence, because we have different initial conditions. We have 3 moles of hydrogen and 1 mole of nitrogen. So they should reach a different level of concentration at the start. maybe they can reach the same concentration, but this does not occur in general. And the third point is very, very important. So during this initial section, the gradient is actually dependent on the mole ratio. We can take the mole ratio of nitrogen gas as a baseline because the coefficient is 1, so it's very easy to compare. So what we should say is that the gradient of this H2 curve should be 3 times steeper than the curve for nitrogen gas. And similarly, the gradient for ammonia is 2 times steeper than nitrogen gas. Perhaps my drawing is not very clear, but you should emphasize this point on your exam. If you are not good at drawing, like me, you can always put this statement beside your graph, and the examiner would award you marks if you do that. Or if you are very good at drawing, you can just show that the gradient for the hydrogen gas concentration is actually 3 times as steep as the gradient for nitrogen gas. And we need to really understand the concept of equilibrium. So I want to emphasize this again. This is a dynamic process. Even if we have reached equilibrium, this doesn't mean our reaction have stopped. It only indicates that the rate of forward reaction is equal to the rate of reverse reaction. So both forward and reverse reaction are actually occurring. And they exactly cancel out the effect of each other. So the forward reaction produces products, and the reverse reaction produces the reactants. And they completely cancel out this process. And that's why they reach equilibrium. I will use an analogy to illustrate my point. If you make $1,000 per week, and you spend $1,000 per week, the result is you have no money left at the end of the week. But this does not mean you did nothing during the week. In fact, you did a lot of things. You have made $1,000 in this week, and you have also managed to spend this $1,000. So you actually did many things during this week. But unfortunately, these two things cancel each other out. So in the end, you do not have any money left. But this does not mean you didn't do anything during this week. So this is the same idea as a chemical equilibrium. You are still working hard to use up the reactant to produce product, and then use up product to produce the reactant. But in the end, these two effects, these two reactions completely cancel each other out. So you need to understand this really, really well, because it is very crucial. If you don't understand this, it will be very hard for you to actually do any of the questions related to equilibrium. Some points to note. Equilibrium only happens in a closed system. So nothing should escape. Imagine the scenario where you let this ammonia gas escape your system. Because ammonia gas exits your system, you do not have any collision between ammonia molecules, since it's no longer there. So you only get forward reaction. In this case, you can actually force the reaction to complete. So you can use up all of your nitrogen gas and hydrogen gas. And we will discuss this later in the next video about how to optimize the yield, so how to maximize the amount of product you actually produce. So this is the topic of another day. So now we only focus on this. We know that equilibrium can only happen when you have a closed system, when the product is actually there, so they can collide with each other and then reform the reactant. If you take the product away, there's no chance they can collide into each other and have equilibrium reaction going on. You can still reach equilibrium if you start with the product. So if you start with a lot of ammonia gas, you can still get equilibrium. It's basically two sides of the same coin. No matter where you start, eventually you will reach equilibrium, if you are in a closed system, of course. Gas pressure and temperature, they are constant at equilibrium. You would expect them to be constant. If the forward reaction is endothermic, the reverse reaction must be exothermic. And then because the rates of forward and reverse are the same, the effect cancel out each other. So one reaction absorbs heat, one reaction produces heat. Ultimately, you should get no overall change in the amount of energy. So the temperature is constant. The gas pressure should also be constant. So for this example, the forward reaction would actually reduce the gas pressure. So you have 4 gas molecules at the start and then 2 gas molecules in the end. But the reverse reaction, you have 2 gas molecules at the start and then 4 when you reach completion. So these two effects also cancel out. So that's why gas pressure and temperature, they are also constant at equilibrium. So that's the 3 things I want you to know. The next topic, we move on to equilibrium law. Note, in VCE chemistry, we only look at homogeneous system. So this means the product reactants are same state. So in the production of ammonia example, they are all in gaseous state. In some reaction, you would actually produce solid from aqueous solutions. And this is not homogeneous system. and we would not consider those types of chemical reactions. So maybe I use some symbols first, and then we can go into a more concrete example. So in this case, the capital letters A, B, C, D depicts concentration. The small A, B, C, D, they represent the mole ratio. And a new topic is a new concept. This is called concentration fraction. So it is the concentration of product C raised to the power of its mole ratio times the concentration of product D raised to its mole ratio divided by, so this is basically the product side, divided by the reactant. Similar idea. So let's have a think of what this concentration fraction is actually doing. If we just perhaps ignore this exponent, it's basically a ratio of your product and reactant. So if you get a lot of product, the concentration fraction would increase. If you get a lot of reactant, the concentration fraction would decrease. So this is how generally you work with concentration fraction. A big concentration fraction means you have a lot of high concentration of product relative to reactant, and vice versa. And of course, this changes during the chemical reaction. Which makes sense because during chemical reaction, the product and reactant, they are changing until we reach equilibrium. So we know that at equilibrium, QC is constant. By definition, at equilibrium, we are not forming any product, nor we are forming any reactant overall. Although like in the individual reaction, we are forming product and reactant, but overall we are not forming any of them. So if the concentration are not changing, and we know the exponent, they are just the mole ratios, they should be constant regardless of the concentration. So QC, the concentration fraction, should be constant. In fact, at equilibrium, QC have a different name. It's called Kc, and Kc stands for equilibrium constant. So another confusion point is the unit of Kc. So the unit of Kc is, this is basically mole to the power of something. And this power is different for every chemical reaction. If you use this hypothetical chemical reaction, the exponent is calculated as follows: C plus D minus A plus B. So essentially it's the coefficient of the product side minus the coefficient of the reactant side, gives you the exponent of the unit of equilibrium constant. We will use a concrete example later. So we can obtain many useful information from Kc. So in general, if Kc is less to 10 to the power of negative 4. We have mostly reactant at equilibrium. If Kc is between those two values, we have lots of reactants and lots of products. If Kc is bigger than 10 to the power of 4, we have mostly products. So this is very useful when in the exam. Whenever they give you an equilibrium constant, you can immediately tell the extent of chemical reaction, whether we would expect to see more reactant or more products in this chemical reaction at equilibrium. We can also get more useful information by comparing Kc with Qc, so comparing the equilibrium constant with the concentration fraction. So if Qc is equal to Kc, we are at equilibrium. This is very simple to understand. It's just a definitional thing. Kc means we are at equilibrium. And if the reaction, the concentration fraction is equal to Kc, then of course we are at equilibrium. Maybe I should emphasize, this is based on our own experiment. So the value of Qc does not necessarily equal to Kc at all times. So we need to measure it ourselves. We need to actually measure, what is the concentration of hydrogen gas? What is the concentration of nitrogen gas? What is the concentration of ammonia in our own system? And since we also know the value of Kc already, we can therefore conclude whether our system is at equilibrium or not. So this Kc really acts as a benchmark for us to compare our reaction to. Because usually for many chemical reactions, especially for gas, they are colorless, they are odorless. You cannot tell whether they are at equilibrium or not. But if you can measure the concentration yourself and you know the value of Kc, you can easily tell whether it's at equilibrium or not. I should also emphasize that Kc is different for different temperature. So the equilibrium constant for the same chemical reaction is different for different temperatures. If Qc is bigger than Kc, what does this indicate? Remember that Qc, broadly speaking, is you divide the concentration of product by the concentration of reactant. So if Qc is very, very big, you have too much product. What happens when you have too much product? You have more collisions between product molecules. So you actually favor the reverse reaction. Another way to think about this is that if QC is bigger than KC, and we know that the system eventually reaches equilibrium, then somehow we are going to decrease the value of QC for it to equal to KC. The only way we can do it is we decrease the concentration of product and increase the concentration of reactant. How do we do this? We favor the reverse reaction, which means we are producing more product. We are producing more reactants. If QC is bigger than KC, you should be able to guess the answer. So QC is very, very small. So this means we have too much reactants. Then we have more collision between reactant molecules. So we favor the forward reaction. Another way to think about this problem is that you need to somehow increase the value of QC in order to equal to the KC. So the only way you can do this is to make product more and then make reactant less. So many ways you can think about this type of problem. Now let's try to do some questions that you may encounter in the exam. So I will give you some questions and then you can work on this yourself and then come back to compare the answer with me. I will also work out the question step by step. So if you don't know how to proceed, you can continue on and watch this video. You need to read the question very carefully. So at 257 degrees, why is this piece of information useful? It is useful because we know that the equilibrium constant Kc is different at different temperatures. And at this temperature, it is 100 mole to the negative 2. So why the exponent is negative 2? Well, we have 2 here, and then 1 plus 3 is 4. And 2 minus 4 is negative 2. So this is also correct. So now the next step. So the next step is to look at the definition of concentration fraction. Remember, if we want to know whether the mixture is at equilibrium or not, we need to compare the concentration fraction with the equilibrium constant. If they are equal to each other, then we know we are at equilibrium. So this is the first step we need to do. So as we recall, the concentration is so this is the formula of the concentration fraction for this particular chemical reaction. And note that we require concentration of those 3 chemicals involved in these chemical reactions. But look at the question we have given. We have 0.1 mole of nitrogen, 0.2 mole of hydrogen gas. So that's not in concentration form. So we need to convert everything into concentration first before we can proceed. So the concentration of ammonia is 0.5 divided by 2 because we have a 2-liter container. So it is kind of being diluted in some sense. So the concentration should be less than the amount of moles present. If we have 0.5 liters, then it's kind of getting more concentrated, so you times this by 2. I know there is a formula for finding concentration, but I don't think formula is useful in this sense because it doesn't help you to understand why we divide this by 2. The concentration of hydrogen gas 0.1 mole. The concentration of nitrogen gas So now we have everything in their concentration. So we can calculate QC very easily. The end result is 1250. What is the unit? Remember, the unit of your concentration fraction should be the same as the unit of your equilibrium constant. So m to the power of -2. So now we can proceed to step 2. So we compare QC, which is 1250, with KC, which we know is 100. So in this case, QC is bigger than KC. What does this indicate? QC is essentially the concentration of your product raised to some particular power divided by the concentration of reactant, also raised to some particular power. The power or the exponent is not changing. So the only thing that changes is the concentration itself. And now we know that the concentration fraction is too big relative to the equilibrium constant. Therefore, we need to somehow make it smaller. How to make it smaller? Well, you need to reduce the number, the concentration of your product and increase the concentration of your reactants. So you favor the reverse reaction. So that's how you solve this kind of problems. Of course, you can memorize. Whenever QC is bigger than KC, you favor the reverse. But I don't think this is helpful in aid your understanding about this kind of problem. And in the exam, if they give you tricky questions, you will not be able to do it because you don't actually understand the concept. Question 2. So this question is actually very easy. You don't really need to do any calculation. To see why, I think it's helpful to write down the definition of concentration fraction again. So it's the concentration of your product divided by the concentration of the reactant. And now the very important piece of information is we do not have any PCl3. So this is 0. 0 times by anything is equal to 0. So this, the denominator is equal to 0. 0 divided by anything except 0, which we know that the PCl5 is not 0, it's also equal to 0. So the concentration fraction is actually 0. And when we compare QC with KC, we know that 0 is less than 1.7. So in this case, we have too little product. And so we will favor the forward reaction. So now let's discuss a very interesting concept, which is also related to the unit of Kc. This is very, very common in multiple choice questions, where they ask you, what is the unit of your Kc? So we have these three identical chemical reactions. They're kind of identical, only differs in very subtle ways. So let's compare 1 and 2. So they look almost exactly the same, but the coefficient of 2 is half the coefficient of 1. So what is the unit for the first reaction? So we have 2 minus 4. So it's m to the negative 2. What is the unit of the second reaction? It's 1 minus 2. So it's minus 1. So as you can see that although we are just changing this reaction slightly, we actually have a different unit of Kc. Maybe I will write one more equation. This is equation 4. We look at equation 4 as well. So the unit is 3 plus 1 minus 2, so m2. So when you are reversing the reaction, so you are making the product reactant and then making the reactant into products, flip the sign. So whenever you have negative, you become positive 2. Whenever you have positive 2, you get to number negative 2. So now let's look at number 3. We have 6 plus 2 minus 4. So 8 minus 4. So the unit is m to the power of 4. So the difference between number 4 and number 3 is that you essentially doubled your mole coefficients. So you went from m to the power of 2 to m to the power of 4. So that's how the unit of equilibrium constant changes when you tweak the chemical reaction slightly. And you should work them out by using the formula I have told you earlier, which is basically you subtract the coefficient of your product by the coefficient of your reactants. So now a slightly more challenging question. Let's have a look at this question. So first, I think I want to emphasize the importance of significant figures. You need to get significant figures right in order to gain marks in the exam. So what is the significant figure of this? So we do not count the leading zeros. So 500, so we have 3 significant figures. For this one, we also have 3. For this one, we have 4. And I should change this to 2.00 liter. This is also 3 sig figs. This is 4. Okay, so we take the least number of significant figures. In this case, we take 3 significant figures. So keep this in mind because you also need to express your answers with 3 significant figures. So we are given that initially we have this much reactant present in our system, in our container. And when at equilibrium, we have 0.14 mole of SO3. So whenever you see those kind of questions, so you see that you're given an initial condition and then you're given, we're at equilibrium and then we have this particular number or amount of a particular reactant or product. You want to use a tool called rice box. Some textbooks say it's ice box, but they are essentially equivalent. So let's have a look. So the first step, always remember the first step is convert everything into concentration. We do not care how many moles of this you have in your system. In order to use concentration fraction or to use equilibrium constant, we must need to convert everything into concentration. So this is your first step. Convert into concentration. So the concentration of S2O2 initially is you can calculate the concentration of oxygen and concentration of SO3. And at the end, you know the concentration of SO3 is so now let's construct the rice box. So R stands for reactants. So you have two. So you need to read off from the chemical reaction they have given you. You have 2 SO3. Put these 2 in your rice box because it will be very important later on. You have 1 O2. Maybe use this to indicate that we are separating the reactant from the product. Have 2 SO3. So I stands for initially. Initially we have, remember everything needs to be written in terms of concentration in this rice box. 0.025, 0.05, 0.075. C stands for change. So we don't know what is the change currently, but E stands for equilibrium concentration. We know that the equilibrium concentration of SO3 is actually 0.07. So now we know what is the change of SO3. So the change, remember the sign is also important. Change is negative 0.005. And now we can calculate the change of oxygen and the change of SO2 because we already know what is the change of SO3. So SO3 and SO2 do have the same coefficient. So their change, the magnitude of their change should be the same. But since we are losing the product, then we must be forming the reactants. Because there's only one way the product can go is you are favoring the reverse reaction. So you are producing your reactants. So this is actually plus 0.005. For oxygen, it's more interesting. The coefficient in front of oxygen gas is half the coefficient of SO3. So you need to halve the change. So you divide the change by 2. So it's also plus because it's the reactant, 0.0025. If the coefficient in front of oxygen is 4, you need to times this the 0.005 by 2. So everything depends on the coefficient. That's why you need to write it in to make it very clear to you. So now it's just a matter of doing some addition. And you get the equilibrium concentration of everything in your system. And so many students, they just end here. But always go back to the question, what are they asking you to solve? They want you to calculate the concentration equilibrium constant. So Kc, remember, it's just a special name of your concentration fraction at equilibrium. So it is calculated as your concentration of SO3 raised to the power of 2 because of this coefficient. Concentration of oxygen, concentration of SO2 is for 12 of 2 at equilibrium. So we are looking at this row here. Essentially 0.07 to the power of 2, 0.03 to the power of 2, 0.075, which is equal to 726. This is 3 significant figures. So it is correct because we require 3 significant figures in our answer. What is the unit? 2 minus 3, so m to the power of -1. So this is how you solve this kind of more complicated problem. I will end this video by emphasizing this point. The extent of reaction, as indicated by the value of your equilibrium constant, is completely unrelated. I will repeat this again, completely unrelated to the rate of reaction. You may have a chemical reaction with a equilibrium constant of 10 to the -4. So mostly reactant at equilibrium, but you can still have a very fast rate. You can have chemical reaction with Kc of 10 to the power of 5, but occurs at a very slow rate. Those two concepts are completely unrelated. So never get confused. If you are asked about rate, think about what impacts the rate of reaction. It's the concentration, its surface area, its temperature. It's whether you have catalyst or not. So that's what affects the rate of reaction.